Right, so we have already seen that in any polynomial ring over a field is a Euclidean ring. So all the results about Euclidean rings that we came across, they are now going to be true in this particular Euclidean ring also. So let us see how the results look. We start with lemma 3. This one says that our polynomial ring is a principal ideal ring. Every Euclidean ring is a principal ideal ring. Since fx is a Euclidean ring, we have already seen, so it's also a principal ideal ring. And by the way, a principal ideal ring, if you recall, is an integral domain with unit element where every ideal is a principal ideal. That means every ideal is generated by a single element, and this fact is going to be quite important when we, for example, study minimal polynomial of a linear operator on a finite dimensional vector space. So that is one place where this fact will be used. And then we have one more result which we already know, which tells us about the existence of a greatest common divisor of two non-zero elements in a Euclidean ring. So if we state that here, then it will look like this. Any two non-zero polynomials fx and gx in fx have a greatest common divisor, some polynomial, again in fx. And we also know that a GCD can be written as a combination of the given elements. So here also the same is true. Plus bx times gx for some elements ax and bx in fx. Note that we are just stating these results in this particular Euclidean ring. So proofs of these results we have already seen when we studied Euclidean rings in general. Okay, now having seen these, next we define something that is like the concept of a prime element in a Euclidean ring. A non-zero, non-unit element fx in this Euclidean ring is said to be irreducible if whenever you are able to write fx as a product of two polynomials. where the polynomials themselves are coming from again fx. Then either ax or bx is a constant polynomial. So that means a I forgot to write one more thing. Irreducible over f if, let me write the if here. That means if you take a polynomial from fx, if it is non-zero, at the same time if it is non-unit, that means it's not a unit in the ring fx, it has no multiplicative inverse in fx, then such a polynomial is said to be irreducible over the field f if whenever you are able to write fx as a product of two polynomials which themselves are of course coming from fx, then exactly one of them must be a constant polynomial, that is exactly one of them must have degree 0. Okay, so that is the definition of irreducibility of fx over the field f. In other words, loosely speaking, fx cannot be factorized non-trivially. That is, if you have found a factorization like this, then one of the factors is trivial in the sense that it's a constant, it's a field element, a constant polynomial. So the degree that fx has is coming entirely from the other factor. Say for example, if ax is constant, fx is irreducible, and you have been able to write fx like this, then say a is constant, then degree of f is equal to degree of bx, because we already know that its degree is the sum of the degrees of 2. So since ax is constant, its degree is 0, so bx will have the same degree as fx. That means we are unable to write an irreducible polynomial as a product of two polynomials of smaller degree. That's the point. So that's what non-trivial, or rather in this case what trivial factorization means. So that is the definition. Now using this definition we can state something which is that unique factorization theorem that we have in a general Euclidean ring, that every such polynomial can be factorized uniquely as a product of irreducible polynomials. But before we go to that, let us also mention that this over f, this is not something we have just simply written for the sake of writing it. It is important. The irreducibility of a polynomial depends on the underlying field. So here we are going to write irreducibility depends on the field in this way. X square plus 1, this polynomial is irreducible over the field of real numbers over R, but is not irreducible over the field of complex numbers. Why? Because you can write x square plus 1 as this product x plus I times x minus I, where I is the square root of minus 1. Note that both of these polynomials have degree smaller than the degree of the original polynomial. Its degree is 2, whereas each of these polynomials is of degree 1. So this is a non-trivial factorization, and as such x square plus 1 as an element of this polynomial ring, it is not irreducible, but it can also be thought of as an element of this polynomial ring, because after all the coefficients are coming, they are in R, and that's why they are complex numbers also. Every real number is a complex number, but here we are not able to write them as a product of two polynomials of smaller degree. These polynomials, note that these are in elements in Cx, however these are not elements in Rx. So although we do have a factorization like this is not a factorization in the ring Rx. Its factors involve polynomials from outside of Rx. So that's why it is irreducible. Actually, that is not the reason it is irreducible. The real reason is that you can prove that this is irreducible over R by considering that it is not irreducible, by supposing and then arriving at a contradiction without ever saying anything about imaginary numbers or things like that. Okay, you can work inside Rx itself. In fact, we are going to come across some such problems when we solve the exercises. So the point here is that this is irreducible over R but not over C. So the underlying field matters. Okay, so now we are going to state the unique factorization theorem version, the version of that theorem in this setup. So this is lemma 395. Any non-zero non-unique polynomial in fx can be uniquely written or can be written in a unique manner as a product of irreducible polynomials in fx. So this is the unique factorization theorem, its version here. And finally, recall the final result from the section on Euclidean rings. We already know that since a Euclidean ring is a principal ideal ring, every ideal is a principal ideal. But in the last result on Euclidean rings, we in fact found a necessary and sufficient condition for such ideals to be maximal, and that was that if you have a Euclidean ring, say R, and there you have an element A, so that you can consider this ideal. Then this ideal is a maximal ideal if and only if A is a prime element in R. Correspondingly, here any such ideal will be a maximal ideal. In our case, R is fx and A is a polynomial if and only if this A is an irreducible polynomial. So that's the statement, and we are now going to state it. So it is lemma 6. The exact statement is this: the ideal A equal to Px in fx is maximal if and only if Px is irreducible over f. So note that since we have said, or we have just stated that x square plus 1 is irreducible over R, so that's why if you consider this polynomial and form the ideal generated by this polynomial in the ring Rx, in the ring of all polynomials with real coefficients, then this ideal is going to be a maximal ideal. So that means if you form this quotient, then this quotient is going to be a field. We have already seen that if you have an ideal in a ring, then the quotient ring is a field if and only if the ideal is a maximal ideal. So that can be applied here, and we can conclude that this is a field. In fact, at some stage we will show that this field is nothing but C, the field of complex numbers. It can be shown very easily. Okay, and we will show, maybe not in these exercises, but at some point we will show this. And this technique of considering an irreducible polynomial in a polynomial ring where a field is given and then forming a maximal ideal and then forming a field by constructing the quotient, this is a standard procedure for constructing fields in general, which we are going to use in the exercises. And here itself, in the next discussion where the section actually ends, we are going to see what it means and what we can achieve with this method. In chapter 5, chapter 5 studies fields in depth. So in chapter 5 we shall return to take a closer look. At this field. Okay, so let us now consider an irreducible polynomial over a field, and let us apply this method to construct the quotient ring, which will be a field, and then we will try to see some facts about that field. Consider the polynomial x cube minus 2 over the field of rational numbers. That means we are considering a polynomial in this polynomial ring. It can be shown that this polynomial is irreducible over the field of rational numbers. In fact, we will show this in the exercises. Okay, so don't worry, we will see why exactly this is irreducible over Q. So the ideal generated by this polynomial in this ring is maximal and as such the quotient is a field. So this quotient is a field, which is just nothing. We are just simply using the fact that such quotients are field if and only if the ideal used to construct them is a maximal ideal. Okay. Now, can we say something about this particular field? Let us try to see how a general element in this field looks like. In a quotient ring, what are the elements? The elements are cosets of the ideal. So that means since our ring is a polynomial ring, so the general element will look like this. This is a coset of the ideal A. Left or right coset, that does not matter, because note that the coset is actually a coset when you consider Qx as an additive group and A as a subgroup. So that is abelian, so left and right cosets are the same, so we just simply say coset and we write fx first. If you want, you can write A plus fx also, considering them as right coset, but we write fx first. Okay, so this is a general element. And now we are going to try to break this element down in terms of this polynomial x cube minus 2. Let me show you what exactly I mean by that. A general element in this quotient ring is where fx is some polynomial with rational coefficient. Now note that since x cube minus 2 is a non-zero polynomial and our polynomial ring, in this we have the division algorithm because it's a Euclidean ring, so we can divide fx by this non-zero polynomial x cube minus 2. Doing that, we will get a quotient and a remainder. They are themselves polynomials. By the division algorithm, there exist unique polynomials say we name them qx and rx. In qx such that fx is equal to qx times x cube minus 2 plus rx, where either rx is the zero polynomial, or if it is non-zero, then degree of rx is strictly less than degree of x cube minus 2. Degree of the remainder polynomial is less than the degree of the divisor polynomial. Now its degree is equal to 3. So that means either rx is 0 or rx is a polynomial of degree at most 2. That means either rx is 0 or rx is a polynomial of degree 0, that means a non-zero constant, or rx is a polynomial of degree 1, or it's a polynomial of degree 2. So in general rx looks like this. a0 plus a1x plus a2 x square. For some rational numbers a0, a1 and a2, because rx is after all a polynomial in qx, so the coefficients will be rational numbers. Now what is the consequence of this form that rx has on this element? Using this form of rx, can we say something about the structure of that general element? In fact, we can say a lot. fx plus a, we now have an expression for fx, so this is qx times x cube minus 2. Okay, don't confuse this x cube minus 2 within round brackets as a. Okay, we have written according to our notation, anything written within round brackets like this is an ideal where the element inside the brackets is the element generating the ideal. Here, however, this is just simply brackets. And if there is a chance of confusion, you can use square brackets also. Plus Rx plus A, and this is equal to, recall the operations in a quotient ring. What type of addition and multiplication do we have in a quotient ring? According to that thing, we have this qx plus a times x cube minus 2 plus a. Let me just not write the bracket at all. Plus Rx plus A. If you find this step confusing, let me simplify it for you. Say you have a ring R and you have an ideal I in that ring. You have formed the quotient R by I. In R by I, the elements are cosets of I that look like this, where A varies over R. Now, what is the definition of addition in this quotient ring? If you take two cosets like this, then this, by definition, this is equal to A plus B plus I. And product is defined like this. Don't write A B times I, okay? The thing that we are getting on the right hand side, that has to be a coset of I. So we need to maintain the operation with respect to which we are considering coset. So that's what we have done here. In place of A and B, now we have polynomials as elements. So if you multiply these two, it will be qx times x cube minus 2 plus A plus Rx plus A. So that plus gives us this plus A, just like A plus B plus I. Okay, now after this step, a simplification occurs. And the simplification is just this. Oh, instead of writing it like this, I could have, okay, there is no need to write it as a product of two elements. Why? That will become clear now. I'm just simply going to write it like this: qx times x cube minus 2 plus A. So this is one coset plus Rx plus A. This is another coset. And this thing is equal to A plus Rx plus A. Now you know that in the quotient ring, simply A itself is the identity element. So if you add that with anything, you are that will vanish. So you are left with Rx plus A. But the question is, how is this thing equal to A? Note that this is equal to A because This will belong to A, but should I write the actual reason first? There is no doubt about this. X cube minus 2 generates A. So in particular, x cube minus 2 is an element of A, and that is because the ring has a unit element. So A has what sort of elements does A have? A has all multiples of x cube minus 2, where we are multiplying x cube minus 2 by arbitrary polynomials. Among all such multiples, you will also have 1 times x cube minus 2, where 1 is the constant polynomial 1, so that is equal to this. So this particular polynomial also belongs to A. Okay, now since A is an ideal, so this element times any element from the ring also belongs to A. So that means qx times x cube minus 2 belongs to A. Now because A is an additive subgroup, so this coset, since this element belongs to A, this coset is actually equal to A itself. Do you remember that if you have a group G and say K is a subgroup of G, then if you take an element K belonging to K, then the coset KK is actually equal to K. That means the coset you are forming by taking one element from the group, if that element comes from the subgroup itself, then you get the subgroup itself. You don't get any new coset. So that's what is happening here. In place of this binary operation that we are not writing here, we have plus. Okay, so that is the reason this is equal to A. So that means instead of writing fx plus A, I can write rx plus A, and now I have an expression for R. So fx plus A is equal to rx plus A, and R is this a1x plus a2x square plus A, and this time we can in fact write it fully like this, using all the operations that the quotient ring has. A0 plus A plus A1 plus A times x plus A plus A2 plus A times x square plus A, which can be written as x plus A whole square because of the definition of multiplication in our quotient ring. Okay, so let us stop here and now try to simplify this even further. Writing t equal to x plus A. Let us denote this coset x plus A by the symbol t. We get fx plus A equal to A0 plus A plus a1 plus a times t plus a2 plus a times t square. Okay, but can we write something else in place of a naught plus a? Of course you can use a symbol and write something, but that's not what I am asking. I am asking, can we write in place of a naught plus a, can we write just simply a naught? You would say, of course that will be a mistake, because a naught plus a is a coset of capital A. However, single a naught is just a field element. So how can we add a field element if I simply, if I replace this a naught plus a by simply a naught, then it does not make sense. How can I add a field element to cosets? That does not make sense. But it can be made sense by identifying this type of elements with field elements themselves. This type means this type of cosets where the polynomial that you are considering to form the coset is a constant polynomial. Let me tell you what I precisely mean by these things. Note that if we define a function f, say, from the field, our field is the field of rational numbers. I should not forget that. This into the polynomial ring by, not the polynomial ring, sorry, the quotient ring by this. Say I take a field element, what should I take? Let me take V. Then its F image is equal to V plus A. If we define a function like this, then it's not very difficult to see that this is a ring homomorphism. That is, it respects addition as well as multiplication, and it also maps the unit element of Q to the unit element of this quotient ring. Unit element of Q is 1, the rational number 1, and the unit element in this quotient ring is the coset 1 plus A. So that thing is true. One more thing that is true here is that this function will be injective. It will be 1 to 1. All of these things mean that we can identify Q as a subsystem in this quotient ring, in the sense that there will be a copy of isomorphic copy of Q inside this quotient ring, and that isomorphic copy consists of elements like this. That is, this is the isomorphic copy of Q inside this quotient ring. Algebraically, as a ring, there is no difference between this set and the set of rational numbers. So, and the isomorphism is brought about by this function where we are identifying V with the coset V plus A. So we can in fact write in place of A naught plus A naught, okay, just the field element. So let us complete what we were writing. Note that if we define like this, then F can be shown to be an embedding. This embedding identifies every field element V with the coset V plus A. With this identification, we have Fx equal to A naught plus A1t plus A2t square. So now look at the coset. It looks something like this. Okay, and there are some facts about this expression or this representation of this general quotient ring element, or in fact this is a field, we already know that, so this is a general field element of this field. So it has an expression like that. It can be written itself as a sort of polynomial of degree, I should not say degree 2, but a polynomial of degree at most 2, or a zero polynomial. Okay, now the first thing to note is that now note what happens if we calculate t cube. T as a coset, its cube makes sense because you are taking the product of x plus a with itself with 3x plus a. So t cube is equal to x plus a whole cube, and that is equal to, by the definition of, okay, don't see, while we are working with these things, it's very easy to lose track of the things and then start doing high school algebra. Say for example, one starts expanding this using the binomial theorem, but that's not what this product means. Its cube does not mean ordinary cube. Okay, it's the multiplication we have in this quotient ring. So it's always important to remember what we are doing. So by definition, this is x cube plus a, not x cube plus 3x square a plus 3x a square. That is not the thing. So this is x cube plus a. Now note that x cube plus a can be written like this: minus 2 plus x, no, not minus 2, plus 2 plus x cube minus 2 plus a. So this is equal to 2 plus a plus x cube minus 2 plus a, and this equals, do you see what is going to happen now? Two plus a in place of, okay, let's just for the moment keep 2 plus a like what it is, plus. Now since we already know that x cube minus 2 belongs to a, so this coset will be equal to a. We have already seen that. So this is equal to a, and a is the identity element in our quotient ring, so this is equal to 2 plus a. And because of that identification of a field element v with this coset, I can write 2 here, where you have to keep in mind that this 2 is actually 2 plus a. So it may be it may look confusing, but this sort of identifications are always used in mathematics. For example, when we write this containment, the set of natural numbers is a subset of the set of integers. Literally it's not a subset, but after an identification it becomes a subset. The thing is that we find a system inside the set of integers or the system of integers that looks exactly like the system of natural numbers in every aspect that matters. Okay, although the two things, that is the system of natural numbers and the subsystem of z, which looks like this system, are literally not the same thing, but for every purpose it can be considered as just like that. It's like considering something and its mirror image. Whatever you do, your image will also do a similar thing. So if looking at the image is enough to say what you are doing, then there is no need to look at you. Someone can look at your image and try to infer what you are doing. So it's like that. So this equality is not literal equality, but it has an interpretation through identification. Okay, so what have we found? We have found that the element t in this field, which is x plus a, is an element whose cube is equal to 2. If you are keenly observing all these calculations, and if you are familiar, you of course should be familiar with this, you know that this equation has no rational solution. There is no rational number x whose cube is equal to 2. Another way of saying that is that the cube root of 2 is not a rational number. I mean, in the system of rational numbers there is no such number. However, we have now, instead of the system of rational numbers, we have found another field where this equation has a root, has a solution, and that solution is t, x plus a. So this is a general procedure of finding larger fields in which a given system, a given equation has solution. For example, this equation has no solution in the field of real numbers. So by following a similar procedure, you can construct this quotient field. Where in this new field, this equation will have a solution. In fact, it will have two solutions, and those two solutions are the imaginary units I and minus I, and you know this field as the field of complex numbers. However, this is not how complex numbers are introduced. We will see more on this later. Okay, so right now we have got an element t whose cube is actually equal to 2 in this larger field. But what about this expression? Is this expression unique? That is the next question. Let us suppose that we have found more rational numbers such that the same element also has another expression that looks like this. Then can we say that they are the same by saying that a naught is equal to a naught prime, a1 is equal to a1 prime, and a2 is equal to a2 prime. So we are aiming to show that that is the case. Then a2t square is equal to t square, or a naught minus a1 plus a naught minus a naught prime is equal to 0, where we should keep in mind that this 0 is actually the 0 element in the quotient ring qx plus a. So that means this is equal to a. Okay. So this is equal to a. Okay, can we conclude that these are 0 from this equation, or should I go back to that original one? That is my question. I think we need not consider this ultimate expression. We can, whatever we have assumed is okay, but then let us go back to the original expression. A naught plus a1x plus a2x square plus a is equal to a naught prime plus a1 prime x plus a2 prime x square plus a. Which implies a naught minus a naught prime plus this plus a is equal to a. Don't write 0 on the right side, okay, because this calculation is in the quotient ring, so the 0 should be the 0 of the quotient ring, and this in turn implies because this coset becomes equal to a. So that means the element used for forming the coset, this polynomial, should be a polynomial in A. Now, what type of elements does A have? A has polynomial multiples of the polynomial x cube minus 2. Since every element in A is a multiple of x cube minus 2 we must have this. But why? Why should this imply that this polynomial must be 0? The reason is that if you take a multiple of x cube minus 2, say you assume that this polynomial is, say, this multiple of x cube minus 2, where hx is any polynomial with, hx is some polynomial with rational coefficients. If hx is non-zero, then what will the degree of this product be? The degree of this product will be equal to the degree of hx plus the degree of x cube minus 2. That means degree of hx plus 3. So the degree will be greater than or equal to 3. Correspondingly, the left hand side, which is equal to this, don't consider this equal to 0 for a moment, okay? The fact that this polynomial belongs to A implies that it's a multiple of x cube minus 2. That's what I am considering here. So then, since this is equal to this polynomial, so its degree should also be greater than or equal to 3. Is that possible? Clearly its degree cannot be greater than or equal to 3. There is no possibility of having a term where we have x cube with non-zero coefficient. So that's why hx cannot be non-zero. Hx has to be equal to 0, and that's why we have that polynomial equal to 0. Okay, but I am not writing all those things in detail. You have got the point. Now a polynomial being 0 like this means what? It means that the coefficients are all 0. This implies coefficients are all 0 means we should have these equalities, and A2 is equal to A2 prime. So the expression that we have for a general element in our quotient ring, which is a field, is actually unique. So is unique. Now if someone wants to show, instead of using the fact that this is already a field, suppose someone wants to show that this is a field, not from theorem. Note that in these calculations we have just simply done one thing. We have expressed a general element in this ring in a somewhat easier to understand form, in a more manageable form. That's what we have done. We have not used the fact that this is a field. So you can either use the previous theorems from ring theory to conclude that this is a field because there is a maximal polynomial, or you can try to directly show that this is a field, and that is the next thing we are going to do. But I think the video has already become quite long, so I am ending it here. In the next part we will see how we can work with this form itself of the general element in this ring and show that if such an element is non-zero, then it has a multiplicative inverse. That will be enough to conclude that this is a field. Why? Because you know that the polynomial ring is commutative, so every quotient ring is commutative. That is one thing. One more thing is that this has a unit element, and that unit element is this, which is not equal to the zero element. This is not equal to a because 1 is not a polynomial in a. So the only thing left to show, to prove that this is a field, is that every non-zero element has a multiplicative inverse. That's what we are going to do in the next part directly, and that will complete this section. The results we will have we will have completed the results once we do that. After that we will see the exercises. So I end the video here. If you have any doubts regarding all the things we have seen today, please feel free to write in the comment section below. So signing off for today, this is me, Lucifer, from a mathematical room. Have a nice night.